focus the talk a bit just on what is our application, because there might be some people who don't know the application, and then on the OpenACC porting aspects, because I saw that there was an introduction into OpenACC in this course. All right, so the title is Getting COSMO Ready for Piz Daint, and I'd just like to acknowledge the whole team. There were a lot of people from ETH, MeteoSwiss, C2SM, CSCS, and also Supercomputing systems involved in this effort. So I'm just standing here as a placeholder. Right, so this is the overview. Oops, typo, sorry about that. I'd like to tell you a bit about weather and climate modeling, so what COSMO is. Then talk a bit about the analysis and what COSMO actually does on high-performance computers. Talk about the approaches we used to port it to Piz Daint, talk about testing, performance, and then draw some conclusions. All right, so when you try to model the weather and climate system, you're actually confronted with what is typically called a multi-scale problem, because in a way you have planetary circulations, which of course you know influence the weather, the low and high pressure systems coming over the Atlantic and hitting Europe. But at the same time, you have processes going on the very small scale, such as the condensation of water droplets or the freezing. And these processes actually have an upscale impact onto the weather. So the latent heat, which is released when water freezes, has an impact on how the weather evolves. So in a way, a model has to cover these scales, and at a certain point, you have to chop off and use what we call parameterization to model the processes that you can actually not really resolve on the model grid. Now, we do have a set of governing equations which basically describe how the fluid of air moves around and how it evolves over time. These are just known as the Euler equations, and they're a set of PDEs. And what is typically one large part of an atmospheric model is the solution of these equations, which basically model the evolution in time of wind, pressure, temperature, all of the water species. So that's water vapor, liquid water, but also water ice in several forms. So ice crystals sedimenting, or ice crystals being small enough that they don't sediment. And then there is an equation for density, which is just a diagnostic equation. We then discretize these equations onto a grid. So we have a mesh, and typically this is, in COSMO, it's a regular mesh, but it's very anisotropic. The reason being that you all know, if you walk up a mountain, the temperatures change very rapidly, but if you walk horizontally for a kilometer, actually the temperatures don't change very rapidly, or very often they don't change very rapidly. So the grid is very anisotropic. In the horizontal, it has typical grid spacings of about 1 to 10 kilometers, whereas in the vertical, very close to the Earth's surface, we have very shallow grid cells, so they're about 20 meters close to the surface, and then they're stretched as you go up. So the grid is very anisotropic. And on this grid, of course, then you get a number of prognostic variables describing the wind, pressure, temperature, the water quantities, and really the COSMO model is about progressing these quantities forward in time using a time-stepping mechanism. Now, we at MeteoSwiss, we run this model, and our applications are typically here. So we have a 7-kilometer implementation of the COSMO model running over Europe. And then inside this European domain, we nest a higher resolution implementation of the COSMO model. And we run this 8 times per day. So every 3 hours, a new run is done. And it runs 33 hours into the future. Now, this is, in a way, this is not a problem which requires a large computer, because it's such a huge problem. But you can imagine if you do a 33-hour forecast and you get the forecast after 5 hours, then you've already lost 5 hours of your forecast. So in a way, you have to go really fast in order for a forecast to be useful. So it's really about time to solution and about throughput, because you have to get these simulations through in a useful amount of time. So typically, for COSMO 2, our requirements are roughly 25 minutes for a 33-hour forecast is what we require. And the problem size we solve and the machine size we actually need really depends critically on the time to solution that we can get. So what is done in terms of production using COSMO at CSCS? What I just talked about is basically our applications from MeteoSwiss, where we have a dedicated system currently where we're doing operations on, and the other system, which is still currently the operational system, is Monte Rosa, which is used for research. Now, the COSMO model is not only used for weather forecasting, it's at the same time a regional climate model, and the ETH and other universities use it at CSCS in order to do regional climate simulations. And interestingly enough, the usage is roughly the same between our operational system and current ROSA. And of course, the goal is now to migrate towards Piz Daint, and I'd like to show you a bit what we did to the COSMO model in order to make it run on Piz Daint in this talk. Now, before moving on to the more technical parts, I think it's always important to start with the driver. So, I mean, it's always easy to say we want bigger and faster simulations, but probably you have to know what the benefit of that is, and I think one of the main drivers for us, one of the main scientific drivers for us is resolution. This is just illustrated here, looking at Switzerland, the Alps, at different resolutions. And basically, what this illustrates is that, of course, if you live in Switzerland and you have all these intricate valleys, you really need a lot of horizontal resolution in order to actually resolve the processes that are going on over Switzerland. So we really have a strong incentive to increase the resolution in order to see events such as extreme flooding in Ticino, or to see events such as strong Föhn storms, which happen over Switzerland. And at the same time, increasing the resolution by a factor of 2 roughly increases the computational cost by a factor of 10. So you can't just double the resolution and do your simulation. It really increases the computational cost by a significant amount. Now, what is COSMO? Well, COSMO is a community code, and as such, it might be a bit different from the typical application you have. I don't know what type of applications you work with, but COSMO is basically used by 7 weather services and over 50 universities and research institutes worldwide. Now, that also means that if you commit something to the trunk, a lot of people really have to be happy with that change. So porting something like that to GPUs can be very painful because you have to bring along a huge community of people, and you can't just do anything you want to the code. And I think that's an important point because it's also been one of the main drivers of the design decisions we made, how we modify the code and how we go about. Probably it's also one of the reasons why we could not be 100% aggressive in terms of the changes we wanted to make, because it's just that if you do that, you also lose performance on all of the other systems that this code is still being run on. Now, as a time-stepping algorithm, COSMO has this very typical time loop. It basically has a huge loop over time. You start with initialization. That's basically reading the initial state of the atmosphere into the model from files. And then you start by imposing some boundary conditions. You do what we call physics. Physics is basically everything that is not resolved by the grid or has to be somehow modeled differently than by the equations. Then we do dynamics, which is the forward integration of the equations I showed before. We have something which is called data simulation. Data simulation is the integration of observations into the model. So you can imagine that if you just integrate forward the model, it will give you fields, but they have nothing to do with reality. From time to time, you have to tell it, oh, by the way, the temperature here in Lugano is this value, and you have to nudge the model towards this reality. So data simulation is the integration of these observations into the model in order to nudge it closer to the real state of the atmosphere. We have relaxation, which is basically nudging the model against the driving model on the outside. Then some diagnostics and input and output. Now, the properties are basically we're solving PDEs, partial differential equations. And we're solving that using finite differences. That's not because we think finite differences are all that great. It's mostly because they're pretty fast. There are a lot of other approaches which are being investigated for dynamical cores of models, such as finite elements or discontinuous Galerkin methods, but this is what we have currently. We run on a structured grid, and the workflow is pretty sequential, so these things are done one after the other. There's no parallelism exploited in terms of the processes that are done on the time step. How does it look like if you would download COSMO and look at the code? Well, you would be confronted with about 300,000 lines of Fortran code. It's Fortran 90. And I've put here the different parts of the code, and you can see that this data assimilation part is very large, and that basically comes from the fact that you have a lot of different observations. You have satellite, airplane observations, radio soundings which are being launched, so balloons, and all of these have to be ingested and pre-processed by the model. So the dynamics here is roughly 20%, and all the physics is 19%. Now, if you kind of do the same chart, but you look at in terms of percent runtime, you see quite a different image. You see that the dynamics, so the integration of the Euler equation, makes up roughly 60% of the total runtime. And the physics, so processes like radiative transfer in the atmosphere or condensation, evaporation of water, makes up 22%, and this huge code here is only 1%. Now this will be important later on, because I think I will show you later on that in spite of this assimilation being only 1%, we have to port it to GPUs, or part of it to GPUs. And I think that's really one of the important points. It's not because your runtime profile looks like this that you can get away with looking just at the large parts. Depending on the characteristics and the properties of your code, you really have to bite the bullet and just port the whole thing to GPU. And I'll try to show that afterwards, why we think we had to do that for COSMO. Now, I'm focusing in on the orange part here, and I just picked out kind of a prototype code of what is typically being run in the dynamics. And this is just a prototype example solving this equation using finite differences. And I cherry-picked, or I ran this across a couple of machines which were available at CSCS. And basically what I tried to show here is if you run this across several hardware architectures, in spite of the number of cores going up, so at the beginning we had 4 cores, and now we have something like 16 cores on a Sandy Bridge socket. If you run the code on a single core, or you scale it up to all cores, the kind of speedups you see when you run a thing like that is not equal to the number of cores. And probably you all know why this is the case. The reason is because this is, or the code doesn't scale with the number of cores, and the reason is that this is very strongly bound by the memory bandwidth. And this is kind of a prototypical example of what COSMO does all the time. So I have an analysis of that code up here. Basically, I count the number of memory accesses. So, oh, sorry, this is the example down here. I count the number of memory accesses. So I have to read A, I have to read B, and I have to write C. I'm assuming that these two, they stay in cache while we do the loop. So I have 3 memory accesses, and I count the number of flops. And I have 5 flops, so I have an addition, a multiplication, a subtraction, a multiplication, and an addition. And if you think about how many flops per byte that gives you, it gives you about 0.05 flops per byte from system memory being read. And if you look at the current GPU, Kepler GPU, it delivers roughly 1,300 gigaflops of compute performance and has a memory bandwidth of roughly 250 gigabytes per second. And so if you want to run at the sweet spot, or if you want to give enough work to a Kepler by reading from main memory, you have to do at least 5.2 flops per byte being read. And this is kind of the punchline for COSMO, or for all the dynamics of COSMO. we are very strongly limited by the memory bandwidth, and that was the main driver of all the optimizations we did to the code, and also of the choice of going to GPUs. Now, I think I would like to put this a bit more into context, because you might have other typical algorithmic motifs. So basically one speaks about the arithmetic intensity, which is just the number of flops per memory access. And if you have a high arithmetic intensity, you're compute bound, and you can usually leverage a high % of peak if you do clever things to your code. If you have a low arithmetic intensity, you're memory bound, so whatever you do, probably you will not leverage the % peak of the machine. You really have to look at the machine as something which delivers a certain memory bandwidth to you, and you have to try to leverage as well as possible that memory bandwidth. And if you put that on a chart like this, I don't know, you might have codes, you choose FFTs, or you might have dense linear algebra or particle methods, or you might want to run linpack. And these really, they basically, if you increase the problem size, the number of flops you do per memory access increases with n. Whereas if you have a code like COSMO, a stencil code, or you do sparse linear algebra, or BLAS1, BLAS2, the number of operations per memory access as you increase your problem size stays constant, because you just increase your grid, but the number of operations you do per grid point stays the same. And this is where we're sitting with COSMO, and this is probably where all stencil codes on structured grids, possibly also unstructured grids, are sitting. So typically COSMO runs with roughly 5 to 10% of peak on a Cray XC30, and we just can't get more out of it. This is already a refactored code which has been optimized to leverage better the memory. So what can you do? Well, you can of course adapt the code to employ bandwidth-saving strategies. You can try to increase data locality. So once a value has been read from main memory, you can try to reuse that value as much as possible. You can do blocking and a lot of other things. You can, instead of reading from memory, you can try to recompute. So you can compute something on the fly instead of store it to a variable. And the other thing you can do is you can try to leverage the high memory bandwidth of specific hardware. And this is really the main reason why we started looking at GPUs for COSMO. Because if you look at the two hardware architectures that today you have on Piz Daint, well, you have a Sandy Bridge socket, which gives you roughly 50 gigabytes per second of memory bandwidth. Or you have a Kepler GPU, which gives you roughly 5 times of that value. So if you have a code which is memory bandwidth bound, going to GPUs is very attractive. Of course, it's not as attractive probably as if you're flop bound, because GPUs are even better at doing flops. But nevertheless, it's a very attractive alternative in order to get higher throughput for a node. Now, probably you've seen a bit what OpenACC can do, and typically the examples you see is that you have this really expensive kernel, so you put some directives around, you port it to the accelerator, and you get the results back. So this is what I call the accelerator approach. It basically leverages the high peak performance of GPUs, and it acknowledges that CPUs and GPUs currently have different memories. So say you have a code, and you get into this region which does lots of flops. Typically what you would do is you would copy the data to the GPU. You would do these flops on the GPU a lot faster, and then you would copy the results back. The result might be something like the density of water or something like that. And as long as this runs a lot faster, then you have gained something by going to GPU. Now you can actually do a very simple argument for COSMO showing that this approach does not work. And the argument is basically that if you look at how much time a time step takes typically in COSMO, so one time step is typically around 250 milliseconds in a production run. And you think about how much time it would take you to transfer 10 prognostic variables, so 10 of the full 3D fields we are advancing in time forward to the GPU, you get that it would roughly take you 118 milliseconds to transfer these fields to the GPU and then back again. And that already shows you that if you go in and you think about this accelerator approach, it just doesn't work for COSMO, because if you have to do that more than once on one time step, you've already lost the full benefit of going to GPU. And so the conclusion here is actually a painful conclusion, that if we want to run COSMO on GPUs and we want to leverage the high memory bandwidth of GPUs, we have to port all code which touches the prognostic variables on the time step to GPU. So even if there is a small part of the code which is just 1% of the runtime, as long as it touches the variables, it has to run on the GPU. Otherwise, you have lost if you have to transfer back and forth. Now, we'd like to shift gears a bit. So this is all just analysis, basically, and showing you why we chose the approaches we have for COSMO. This is another example which is also a motivation for one of the approaches. And it's basically picking out a code example from COSMO, a solution of the tridiagonal linear system. And this is abundant in COSMO, so it appears all the time. We have tons of these solvers. They're used for vertical advection, for diffusion, and for radiation. And so this kind of algorithmic motif is abundant and is performance critical for COSMO. And I just picked out the COSMO version, so you don't really need to look at the code in detail. It's the Thomas algorithm. You do a forward elimination and a back substitution, and the code is actually a bit simplified from what is really in COSMO. Now, if you think about giving this code out to a computer scientist and you tell him, please optimize this for x86 hardware architectures, well, he will kind of go out, he will change the data layout, he will change the parallelization, he will change the loop order, he will introduce blocking, he will remove these directives, which are for vectorization on a vector machine, and he will probably parallelize using OpenMP. And then you kind of go to another computer scientist and you do the same exercise and you say, now please optimize this code for GPU. Well, if you're lucky, he retains the Fortran language. Probably he will switch to some other language like CUDA. He will change the data layout again. He will change the parallelization. He will remove the blocking. Loop order will be different. He will do SIMD vectorization using threads, and he will insert OpenACC directives. Now, the kind of learning from this is that there's kind of, if you take your code and you optimize it in the way I just described, there's no separations of concerns. Your code will end up being a mix of mathematical model, numerical discretization, but a lot of hardware-dependent implementation details. And the other big point here is that actually the optimizations are not compatible. So the kind of data structures and loop orders you have are not the same on GPU and in CPU. And if you have a community code and you want to retain the ability to run efficiently both on CPUs and on GPUs, you're kind of in a fix here. So the consequences are that it's actually hard to achieve performance portability with a single source code. It's hard to understand and modify the code if it's been highly optimized. It's hard to validate and debug, and also hard to reuse because you can't just pick it out and give it to some other weather model because it will be very specialized for some hardware architecture. So is there an easy way out? So what people typically do when they have a situation like this is they look for libraries. So they go and try to see is there some library which does what I want to do in an efficient way. So can we, for example, replace the tridiagonal solve with an efficient hardware-specific implementation or a library call? So basically, the prerequisite for that would be that my runtime profile looks like this, that all of this is tridiagonal solves, the rest is a bit of dynamics and I/O, and I can replace this with a library call. And the answer is, well, this is not really the case. The cost of moving the data into the library is actually excessive. It's not worthwhile copying your data into the format which is accepted by the library. Okay, I have to put the caveat here that is if your library has a callable interface and fixes the data structure. There might be other approaches for libraries out there which actually work. But it's also that we don't have a single hotspot. So, I mean, we don't just have tridiagonal solves. We have a lot of other stuff. And so this doesn't work. And basically, for COSMO, we have some basic entities, which I call prognostic variables. And we perform a series of expensive operations, such as advection, diffusion, physics, on them every time step. And somehow we have to replace all of that. And there's currently no real library out there which I can replace all of that by a call. So what are the solutions? Well, you can try to go for compromise. Maybe you don't need the last 20% of performance. Maybe there's some kind of good compromise. You can, of course, go for several source codes, or you can try to separate the model and the algorithm from the hardware-specific implementation and optimization. And I'm definitely not the one who can do that. I'm a domain scientist, but this is basically the route we try to take for the dynamics. So for the dynamics, or for the solution of the Euler equations, I showed you this takes up about 60% of the total runtime, and it's about 40,000 lines. Here we actually have the situation that there's quite few developers. So this is not a code which changes every day, and there's only about 3 people who actively work in this part of the code. And I've tried to motivate that this is a part of the code which is strongly memory bandwidth bound. And here we chose to actually do an aggressive rewrite. So we got rid of saying it has to be in Fortran. We wanted to change the data structures, and the approach we used a domain-specific library, which is called STELLA. Now, I don't think in this talk I want to focus much more on this STELLA library. I'd like to focus more on the other part, but basically the punchline is that using this library, we have 2 backends, one for CPU and one for GPU, and within the library, we can change the parallelization, we can change the storage, and basically it's possible to switch between the backends without modifying the user code. So without modifying the dynamics code, you can actually switch between different hardware architectures and different optimizations. So basically what happened is we had this user code here, which was the dynamics before, and we built up this library which has different backends, and the user code actually got a bit smaller because all of the details of CUDA, OpenMP, blocking, and things like that are hidden down in the library, and we have a pretty plain vanilla specification of what the code should do in the dynamics, and a lot of the hardware-dependent optimizations are hidden in here. Okay, I think that's all I would like to say about this. There's actually people sitting in this room who can answer the questions concerning this library a lot better. So if you're interested in this DSL approach, we have some presentations about it, and you can also ask the people who are here later. What I would like to focus in a bit more is like the rest of the code, so physics, assimilation, and all the rest. So this is quite a lot of lines. It sums up to roughly 25% of the runtime. There's quite a lot of developers here, and we typically do plug-in from other models. So we get some module, and we want to plug it into the code. So changing the programming language really was not an option here. And it's also a little bit less memory bandwidth bound. So here we decided to port it to GPU by retaining the source code and using OpenACC directives. Now, the way this is done is basically before going into the time loop, we have this huge data region saying, please copy in all the variables which are being used. And this is copying all of the variables to the GPU with the goal that these variables do not need to be copied back and forth during the time stepping, and the data region actually ends after the time stepping. So all of the initialization has not been ported. Basically, we just do the initialization, and then we copy all the fields to GPU using a huge data region here. Now, then, for the physics, for example, we port using OpenACC directives. We do some code optimization, and some of the critical routines currently actually have a CPU and a GPU version because it's not possible to retain always the same source code. And the way this typically looks like is we enter a region, and there's a data present asserting that all of the fields we need are actually present, and then we just have the OpenACC directives. Now this has quite a lot of consequences in terms of safety of the programming approach, because if you forget these directives, your code will actually run without problem. It will modify the corresponding fields on the CPU and will give you the wrong results. And it's actually, if you have a very complex code, it's actually very hard to find out all the places where your fields are being touched. So it's, I mean, people, when they teach you OpenACC, they teach you, here's your kernel, now port it, and it's very easy to port it. You just move the data over back, and you have everything on one page or one terminal. But reality is a bit different very often because here data management is really an issue because you have to make sure, well, first of all, you can check that your fields are on the GPU, but if you forget to parallelize one loop which touches a field which is on the GPU, there's just no way currently to check whether this is happening except systematic unit testing. Okay, so how does, this is just a performance slide for this physics part, which we ported using OpenACC, and basically this is comparing an Interlagos, so an old hardware, to a Kepler for a typical test case, and basically what this shows you is that, I mean, a lot of people show speedup numbers, but it really depends on the type of characteristics of the code, what performance you will get. Typically, turbulence is very memory bandwidth bound, and we're happy if we get something like a factor of 3, whereas microphysics is pretty compute bound, and so there you can expect something like 6 to 7. So it's not because you get different speedups than what the other people tell you that something is wrong with your code. It really depends, and it's worthwhile analyzing the structure of your code in order to find out whether you're doing a good job or not. So what do we do for the dynamics? Well, I told you here we have a complete rewrite using CUDA, and somehow we have to make this C++ CUDA talk to the Fortran part using OpenACC. And the way this is done is basically there's a directive which can be used in OpenACC, which is called host data, use device, and that basically allows you to access the GPU pointer of a field. Now, so the way this is done is basically we get the GPU pointers of the fields we want to access, and then we call the dynamics, which actually runs in C++ CUDA, and we pass it the GPU pointers of the data, and then here's the end host data directive. So this is basically the key to making CUDA and OpenACC interoperable. For a very long time, this was not available, and it was actually, you needed some hacks in order to get the GPU pointers out. So the punchline here is with this approach, you don't need any copies from going from Fortran OpenACC to C++ CUDA, and you have interoperability and you can share the fields. Okay, so for the rest of the things on the time step, we basically ported also with OpenACC directives, and since these are not critical in terms of performance, we basically just said here we do little or no code optimization, and we retain strictly a single source code. Now, nevertheless, data assimilation is about 150,000 lines of code, so we had to go through these 150,000 lines of code and see where are these fields actually touched and what do we have to port or not. So using this approach, you end up doing quite a lot of porting work for something which is not performance critical. Okay, input-output. Basically, the I/O we left on the host, so on the CPU, because it's not done every time step, it's only done every nth time step. So here we copy back to the host, and the fields which are read from file, we copy them to the device. So what was our experience with OpenACC? I think one thing which is really nice, it allows you to retain an existing user code. If you're lucky, it actually allows you to just insert directives. Our experience was very often we nevertheless had to do restructuring of the source code. It's relatively easy to get the code running and validating. You can do it progressively as you go. You can start with a small data region, expand out as you go. And it's useful actually for large code bases. Nevertheless, getting out performance may require significant restructuring, and in most of the cases where we really wanted to get high performance, we currently have two source codes, one for GPU and one for CPU. Data placement can be tricky. The programming model does not really give you a lot of help determining where your data lives at the current moment, whether it's on the CPU or on the GPU. So this was one of the main issues in terms of debugging the code. The compiler support is continually improving, and we got a lot of help from the vendors. So if you actually use this and you run into trouble, I would advise you not to hesitate to ask. And as compared to the other approach which we used for the dynamics, of course, with using OpenACC, you trust the compiler to do a lot of things for you. So basically the data placement, register allocation, and things like that. You just trust your compiler to do the right thing, and sometimes he doesn't do the right thing. Very often he does, but sometimes he doesn't. So if you're really interested in getting the last % of performance out, OpenACC might not be the right choice. I think I would like to make one last point about testing, because this was also one of the learnings coming out of this project. I think it's really worthwhile to think about testing before you actually start porting any line of code. It's important to realize that you can often not expect bit reproducible results between your rewritten version and your reference version, or between your CPU version and GPU version. In spite of GPUs adhering to the IEEE standard, the implementations of transcendental functions, square root signs, exp, logs are not the same. So you will get different results, and you should think about how to validate whether your results are correct. In a weather model, a small difference can grow into a large difference. You all know the butterfly effect. So if you have a small difference, all of a sudden your weather can be completely different. And it's actually quite hard to distinguish coding errors from natural error growth in your system. And I don't know if that will be the case for you, but I think our kind of learning was that rigorous unit testing and regression testing should be automated. It should check the validity and performance, and it should check as many use cases as possible. For a too long time, we didn't do this and went through the painful process of trying to find bugs and errors related to us simply not catching that this was an error. We saw some differences and we said, oh, that's fine, that's we ported it to GPU, but it was actually not the case. So the thing we did is we developed a serialization framework, and that basically allows you to write out objects or data fields into a file, and it allows you to compare specific operators against the reference version. So say your reference version is a CPU implementation, and here you compute this advection operator. What you do is you can serialize out the inputs and the outputs into this operator, into a file, and then you can unit test it. So you can have your rewritten code. So this would be your code running on the GPU, and you can read the information from the file. You read the input. You set up the test, you run your operator on GPU or your rewritten operator, and in the end you assert that the result is equals to the reference or is within a certain error threshold of your reference. And you can do that for small code units. That really helps you a lot in speeding up the process of porting to GPU. Okay, so I'm almost there. I think to end the talk, I would just like to show you what all the effort brought for us. Basically, this is a plot which has been produced by CSCS doing time-to-solution measurements and power measurements on COSMO. And it was running a production case of COSMO, so a COSMO 2 implementation on a rack. And it has been done across several generations of machines. So basically, in green, you see the current production code. So that's the current Fortran code without all of the refactoring that we did. And simply by refactoring it, but still running on Monte Rosa, but being more careful about memory bandwidth, we roughly got out a factor of 1.4. Now, if you instead of just using the new code, you use the new code on GPU, so this is 30. You get out an additional factor of 1.8. So all the effort of porting the code to GPUs when going from Rosa to 30 brought us roughly a factor of 1.8. Now, at a certain moment, the first Piz Daint came out, which was a pure CPU machine at the time, and just going from Rosa to Piz Daint using 2 Sandy Bridge sockets gave us a speed up using the Fortran code of roughly 1.35. So this speed up here is basically if you would have done nothing to your code and just sat there and waited for CSCS to bring you a new machine, this is what you would have gotten out of running the same old production code on CPUs. Now, if you run the new code, on top of that, you get a factor of 1.5. And if you go now to Piz Daint, the hybrid machine, you roughly get an additional factor of 1.7. So overall, for people who were doing production on ROSA until now, when they switch now to hybrid Piz Daint, and they leverage the GPUs using the code, they roughly get out a factor of 3, a little bit more than 3, depending on the use case. Now I think this chart is really interesting because it kind of tells you what you get out in terms of just standard technology improvement, what you get out in terms of disruptive technology improvement, and kind of what you can get out if you really make an effort in your code in order to port it to hybrid architectures. The story for MeteoSwiss is actually not only about time to solution, but it's also about energy. I think we currently have about 20-ish% or 25% of our budget going into the energy bill. So we don't only pay money for the machine, but also for paying the electricity bill of the machines. And by going to GPU, the overall story is that we could reduce the energy to solution by roughly a factor of 7, because GPUs are just much a more energy efficient platform. And so by doing that, we could really leverage all the effort going into that. So at the end, as always, I like to kind of, so this could have been seen as a publicity for GPUs, right? So at the end, I would like to take a step back and kind of make a point that it's really important to be aware that your optimal hardware depends on the use case. It really depends on what you're interested in. So for atmospheric models, sometimes you have a fixed problem size and you want to run as long simulation as possible. So you cannot increase the number of grid points, you don't have a lot of parallelism, and you really want to do strong scaling on this problem as much as possible. Now when you do that, actually, this is a chart showing you the number of grid points per node, and this is the wall time to solution. This is just for the die core, but the plot looks exactly the same for the overall code. And what you can see is that the GPU time to solution goes down, scales well, and then starts to saturate. And the saturation comes from the fact that if you have too few grid points per node or per GPU, you actually don't have enough parallelism on the GPU in order to use it effectively. Whereas on the CPU, which is much more of a kind of a scalar processing unit, you actually scale down much further. A single core is actually happy to work on a single grid point or on a couple of grid points. So you can, by using CPUs, you can actually scale down much further. And currently, you can, if you're really just interested in time to solution on a fixed problem size, you can get further with CPUs. So this is kind of your throughput mode, and this would be your high performance mode. And depending on the use case you are interested in, say you want to do a climate simulation for 1,000 years, then probably you're much more in this mode here. Say you want to solve a very large problem for only 1 day, and then you're probably much more in this high throughput mode. It happens to be that MeteoSwiss is sitting pretty much here in this throughput mode, and this is where GPUs are actually very attractive. But depending on your use case, you might actually find out that the optimal hardware for your use case might be different. Okay, so what are the conclusions? Well, I think the effort of the past 3 years has shown that it's feasible to progressively adapt about 300,000 lines of weather and climate code to hybrid architectures. We haven't ported them all. We tried to pick out the ones which are important and which need to be ported. The technologies are ready and are becoming robust. We have robust CUDA and OpenACC compilers. We can do G2G communication. I haven't talked about that, but that's something we leverage. Something which was also kind of an exercise or an experience for us is GPU porting is actually accessible to domain scientists. So you don't necessarily need to be a computer scientist to do that work. A lot of the people in our team came from plasma physics, or whereas me, a domain scientist from meteorology. So as long as you program on a high level using OpenACC or on top of the domain-specific language we developed, it's actually quite feasible to just be a domain scientist in order to port for GPUs. I think one thing we underestimated was the complexity of the heterogeneous code in the end. We had CUDA, we had C++, we had Fortran, OpenACC, and all that had to somehow go together and work together. And I think for quite a long time, we were actually not really aware of how big the effort is of integrating this rewritten dynamical core into the existing Fortran code. And the other, yeah, exactly. So this is an underestimation of the effort to integrate all of these technologies. Right, and I think that's it.